Alright, let's get started with question 12. Now, I've made you guys another 3D model for this one because I thought this diagram might be a bit confusing for some people. So, here's the diagram, and I'll just rotate it a bit so you can see what's going on here. So that triangle is like standing up straight on this graph. So the volume, the solid that we're looking for is composed of like infinitely many of these triangles going all the way from there up to here. So that's going to look like this. So I'll just rotate this a bit so you guys can get a feel for what this solid looks like. So the way that you would work out the volume of that solid is you'd imagine cutting it into these triangles again. So I'm just going to make the triangles a bit chunkier than the original triangle so that we can think about the volume of each one. So if you wanted like an approximation for the volume of the solid, you could just cut it into finitely many. I think I've done 20 triangles here. So I'm just going to pull one of them out so that we can think about the volume of that. So the sort of thickness of that prism is, you know, whatever you choose it to be depending on the number of triangles. So I'll just call that delta y because it's the change in y as y is going along there. And then this side length was 1 minus y squared because that was the graph of 1 minus y squared. And volume of a prism is just that thickness times the area. So for that triangle you can do half AB sine C, or you can work out the height of it from knowing that that's 60 degrees since it's equilateral, and also that side length is 1 minus y squared. So you can do sine 60 as the height over the 1 minus y squared, and that'll give you that the height is root 3 on 2 times 1 minus y squared. And then if we're doing half base times height, so we've got half of that times the base, which is 1 minus y squared again. So that'll be squared there. And then the volume of the prism is that area times the delta y. And then we just add all those up. So that's for one prism, and then for all of the prisms, you just do the sum. So that would give you a good approximation for it. If you're imagining the limit of that as the number of prisms increases, then we just have long s instead of the sigma, and I'll just simplify that as well. 3 on 4, 1 minus y squared, squared, and then we just write dy instead of delta y if it's like an infinitely small change in y. And that's running from, that was -1 up to 1. So we just need to work that out by doing the antiderivative. I'm going to pull the root 3 on 4 out the front. And then let's expand this, because, yeah, we can't really integrate it in the form it's in now. So if we expand that, we get 1 minus 2y squared plus y to the 4th dy. And then that's going to make, so the 1, when you do the antiderivative, becomes y, and then you've got minus 2 on 3 y cubed plus 1 on 5th y to the 5th. Oh, why did I write those there? I have no idea. Okay, and then we just need to plug those values in. So we have root 3 on 4, just the 1 into there, minus 2/3 times the 1 cubed, which is just 1, plus a 5th times 1 to the 5th, which is just 1. And then we need to subtract that with -1 plugged in, which is actually just going to make that same thing but negative, because these are all odd powers. So if we're subtracting that same thing but negative, those two negatives are going to cancel, and you're just going to be adding that same thing again, so it's just like that times 2. You can also think of it as like, just work out half of the volume, like from 0 to 1, and then the bit down here will be the same volume again. So it's 2 times the integral from 0 to 1. Okay, so let's just simplify that. 1 minus 2/3 is 1/3, and then 1/3 plus 1/5 is 8 on 15. And then let's cancel some common factors there. So 4, and that becomes 2. And then 2 times 2 is 4, 4 root 3 on 15. So that's the volume of the solid, 4 root 3 on 15. Okay, part B. So implicit differentiation just means that you differentiate both sides of the equation, in this case with respect to x. So on the left, you'll get 2x, is the derivative of that. And then for this bit, we have to use the product rule. So the derivative of the x is just 1, so 1 times the y. And then you'll have the x times the derivative of the y. And just remember that we're differentiating with respect to x. So that's going to be dy by dx. And we don't know what that is yet. So we're hoping to get an equation that we can then solve for dy by dx. Okay, so that's that bit. And then this one, if you kind of have to use the chain rule here, because we can differentiate that with respect to y, and then we have to multiply by dy by dx. So we'll get 2y times dy by dx. And then on the right, just remember that the derivative of a constant is 0. I think everyone makes the mistake once or twice of just going, okay, that's 3. But yeah, we have to remember constants when you differentiate them make 0. Okay, so we've got 2x plus y, and then if we want to solve this for dy by dx, what we need to do is like factorize this bit so that there's only one dy by dx in the equation. So make that x plus 2y times dy by dx. And then we can move that over, so I'll just negative 2x minus y there. And then we can divide by that to solve for dy by dx. And then, oh, I've actually got the negative out the front. So negative 2x plus y divided by x plus 2y. Yeah, and that's it. Okay, so for part 2, we want to set this to be 0 and solve that. So we've got 0 is negative 2x plus y over x plus 2y. And then if you multiply both sides by x plus 2y, then on the left you're just going to get 0. Actually, let's get rid of the negative as well. We can multiply both sides by negative 1. And then the left is still 0. And on the right we'll have 2x plus y. So we could solve that for y. Y equals negative 2x. So what we can do now is we need a point that's actually on the curve. So not every point that satisfies that equation will be on the curve. So what we need to do is take into account that equation as well. So we need to combine these two and solve them simultaneously. So I'll just plug that in there. So we get x squared minus 2x squared plus that squared, which is plus 4x squared, equals 3. And then that makes 3x squared. And so x squared equals 1, and you get x equals plus or minus 1. Don't forget the plus or minus, because you will lose marks. Okay, so then we can just work out y using that. So when x is 1, you'll get y is negative 2 times 1. And when x is negative 1, you'll get y is negative 2 times negative 1, which is positive 2. So the coordinates of the points are 1, negative 2, and negative 1, 2. That's the answer. Part C. So I've just pasted this from the formula sheet, so that's in the further integrals section. We're going to need that for this question. So what I would notice with this one, like we can't integrate it when it's in its present form. We're going to have to change it somehow. So what you can do is think of the x squared plus 2x as being like the same as the bottom, but then minus 5. I mean, essentially what we're doing there is polynomial division, but just not in the fancy way that we normally do it. So if you think of that as like being that divided by that, and then minus 5 divided by that, that's going to make, like that divided by that is 1. And then you've got minus 5 over the x squared plus 2x plus 5. So, I mean, really what I did there is work out that this divided by that is 1 with remainder negative 5, but just not in the normal way with the division thingy and so on. Okay, so we're going to work out how to integrate that. Now, what I would notice is that it's kind of almost in this form, but not quite. So what we could do is complete the square here, and then we'll have something squared plus a constant, just like in here. So we've got, actually let's integrate the 1, that'll make x. And then we've got minus, I'll bring the 5 out the front. Minus 5 integral of 1 on. Now this is x plus 1 squared. That would make x squared plus 2x plus 1. So I have to add 4 to that to make it into that. Okay, now if you're confused about how to integrate that with the x plus 1 in there, what you could do is do a u substitution. You could say let u equals x plus 1, and then du by dx will just be 1, so du equals dx. So you can say that that's x minus 5 integral 1 on u squared plus 4 du. And then, so that's our a squared. So a will be equal to 2. So you get x minus 5 times this, which will be 1 on 2 arctan of u on a. So u is x plus 1. Let's put that in. And then a was 2, and plus a constant. So yeah, you can do that. I personally didn't actually bother with the u substitution. I just sort of thought, okay, if the derivative of that is that, then the derivative of that with x plus 1 in there instead is going to be that with x plus 1 in there. And then by the chain rule, you would multiply by the derivative of x plus 1, which is just 1. So I basically just went straight from that to there. But if that confuses you, you can use the u substitution. Okay, so we're pretty much done. I'll just make that into 5 on 2. Arctan x plus 1 on 2 plus c. And that's it. Part D. So I'll just draw these graphs on top of this one so you can see how these things change this graph. So for the absolute value one, absolute value of a positive number is just that same number, so that's not going to change these regions where f of x is positive, so those are just going to be exactly the same. But for this bit where f of x is negative, what's going to happen with that is it's going to be sort of reflected up to here. If you get confused, you can always just like pick a random point. So, we could look at this point and see what happens to it. So f of x there is a negative number. If we do absolute value of that, it's going to be like up here instead. So that point gets like flipped over up to there. And that's going to happen with all those points. So it's going to look like this sort of mirror image of that. So this is the graph of absolute value of f of x. Same asymptotes, same intercepts, just that one intercept. And yeah, so that's it for that one. For part 2, f of x squared. So what we can do is we can look at some individual points and see what's going to happen to them. So this one, for instance, that's got a value a bit less than 1, so when you square that, that's actually going to make it smaller and push it down to here. So all of these are going to be like pushed downwards, and even more so as we approach 0, because the smaller f of x is, the smaller f of x squared is going to be, if that makes sense. So that was not meant to go below the x-axis. That's just going to go like that. And then for these values, they're going to become positive because negative number squared is positive. So it's going to be going like that. And yeah, just approaching positive infinity instead. So it's not the exact same shape because it's going to be kind of, yeah, flatter there and growing faster here than it was there because it's squared. Over here, we've got numbers that are like a bit bigger than 1, so when you square them, they're going to be pushed up a little bit. So it's the same sort of thing, it's just a bit higher. And it still has that same asymptote of y equals 1. So that's the graph of f of x squared. Same asymptotes again, same intercepts. Not much change there. Okay, so for part 3, which is x plus f of x, let's look at a few points and see what happens. So 0, for instance, that's now just 0 plus 0, so that's still there. We could look at, say, x equals -1. Let's see what happens to that point. So it's now -1 plus that value, so it's going to be pulled down to there. And at -2, a similar thing, but that's going to be pulled down by 2. So sort of there. For values in here, it's kind of hard to see, are they going to go above the x-axis or is it going to stay below? Maybe it's going to go above the x-axis here, like that. So let's see if we can find if there's other intercepts. So let's go x plus x on x minus 1 equals 0. Let's multiply both sides by x minus 1, x squared minus x plus x equals 0. Those cancel, and then you just get x equals 0. So there's actually just that one intercept there, and so it doesn't like go above the x-axis at all there, it just stays like that, going down like that, and this bit is just going to be like a little bit higher than this because x is positive in this region, but just pushed up a bit, but it's still going to have that asymptote because when x is like, I don't know, 0.9, say, you're going to have this really big negative number plus 0.9, so it's still going to be a big negative number. Over here, we could look at, say, x equals 2, see what happens. So you've got that plus the 2, so that's going to be like pushed up to here. And if x is 3, for instance, this one's going to be pushed up even higher. So it's going to be doing that kind of a thing, where it's still got this asymptote here. And so now you can see we've got this diagonal asymptote. So let's think about why that is. When x gets really big, either positive or negative, x plus f of x, the f of x tends to 1, so it's like x plus 1. So if we draw in y equals x plus 1, which is a line like that, that's our asymptote now. Yeah, so we've still got the x equals 1 asymptote. This one is now y equals x plus 1 instead of y equals 1. And we still just have that one intercept there. So that's our graph of x plus f of x. Alright, that's it for question 12. So give this video a like if you want me to make more like this, and stay tuned for question 13.